All right, so this is the fun part, adjusted R squared. So here we've got a simple linear regression. We've talked about how the R squared is derived. So what the formula for R squared is, it's equals to 1 minus sum of squares of residuals divided by total sum of squares, where sum of squares of residuals is the sum of squares of the distances from the observations to your fitted line. So we don't see it here. That's your simple linear regression line that we fit onto our data, and the total sum of squares, we can see it here. So that's the total, the sum of the squares of those red lines we can see here. So the difference between your observations and the average. So basically R squared is telling us how well is your model fitted to the data, and in fact how much better is it fitted than the average line that you can just draw through your data very easily. So let's get rid of all of that and put our R squared formula on the left for a second. Now, we talked about R squared for a simple linear regression. Well, the same concepts apply for a multiple linear regression. So for instance, with two variables, R squared would be calculated in the same way. We're just not going to go through all these derivations right now because it's just easier to visualize the way we've done it, and exactly the same concepts apply to a multiple linear regression. And still, so what that means is that the all ordinary least squares method is used, and the best fitting multiple linear regression is the one that has the least sum of squares of residual. So you're trying to minimize the sum of squares of residual. And why am I bringing that up? Well, we'll need that in a second. So we want to use R squared, as we discussed, as a goodness of a fit parameter. So the bigger it is, the better. The closer it is to 1, the better your model. And that's awesome. We can totally try doing that, but there is one problem. And the problem is, or starts to occur, when you add more variables to your model. So here you can see we've got two variables in our multiple linear regression. What will happen if we add a third variable to our model? Think of it as an example. Let's look at that example with salary. So your salary equals to a constant 30,000 plus 10,000 times the years of experience, plus, for instance, B2 could be a constant coefficient times the number of qualifications you have, and I don't know, B3 could be how much money you brought the company in the previous year. So if you're a salesman, for instance, so a coefficient times the amount of dollars that you brought the company in the previous year, something like that. So you can keep adding on variables that you think are actually impacting the outcome, so are impacting the dependent variable, and you want to fit a model and see, you know, if it's better or not. So in this case, we're adding a third variable. We already have a model with two variables and it works okay. And now we want to add a third variable and see if maybe using the third variable, we can fit our model even better. So we can create an even better model with three variables. So how can we judge that? After we've added our variable and we've run the model, we can look at the R squared. Did the R squared get better or worse? So in fact, did the R squared increase, or did it decrease or stay the same? So the problem here is that R squared, because of these two things, R squared will never decrease. And let's go through that in a bit more detail. I'm going to use my mouse here because this is quite an important part. So R squared over here is equal to 1 minus sum of square of residual divided by sum of square of total. So once you add a new variable to your model, right, is going to somehow affect what the model looks like. And the fact that we're trying to minimize the sum of squares of residual, what that means is that either this new variable will help minimize the sum of square of residual, somehow the regression process will find a way to give it a coefficient that will help minimize the sum of square of residuals, and then and in that case, R squared will happen to R squared. It'll be 1 minus something that is less than it used to be, right? Divided by the same value, because by adding a new variable, we're not affecting the observations, we're not affecting the averages of the observations, right? This does not change. So by adding a new variable, the regression process through this condition will definitely try to minimize this value, make it even smaller than it is currently. And that way, this whole part will decrease and this whole part will increase. So your R squared will increase. If it so happens that the new variable that's added, whatever coefficient you give it, a new coefficient you give it, if you cannot decrease SS residual, right, what will happen? Well, this coefficient will just become 0. It rarely happens. I don't think I've ever seen a coefficient like be exactly 0, and I'll tell you just now why. But in the worst case scenario, the regression process will say, nah, this variable is, you know, completely just making the world model definitely worse, so I'll just put a 0 instead of this coefficient and forget about it. And that way SS residual won't change and R squared won't change. So you only have two options. Either R squared will increase or it won't change at all. So R squared will never decrease if you add variables. And why I say that B3 is never equal to exactly 0, because there can always be, or there will always be at least a slight random correlation between the independent variable and the dependent variable. It doesn't matter what you put in here. So even in the example when we're looking at salary, so salary equals years of experience plus how many qualifications the person has, and then we can add in what is the last digit of the person's mobile number, right? Of course, that is not going to, it doesn't have any correlation with the independent variable whatsoever. Well, there's no causative factor, there's no association between the two. The last digit of your mobile number has no effect on your salary. But if we add it in, and there will randomly be a slight correlation, you know, it'll just be a random correlation, and the regression process will pick it up and will give it a coefficient, and R squared will probably decrease by that tiny little, or increase by that tiny little bit. And so that is why there's a problem with R squared. You can add variables and you will not know if those variables are helping your model or if they're not helping, because your R squared is biased. It's basically always increasing regardless of the actual improvement or non-improvement in fit. So we got to come up with a different parameter to measure goodness of fit, and that is where adjusted R squared comes in. And this is the formula for adjusted R squared. Here, P is the number of regressors, so the number of independent variables, n is the sample size, so it's over here. Now they say that adjusted R squared has a penalization factor. It penalizes you for adding independent variables that don't help your model. And let's talk about that. That's the important bit about adjusted R squared. So P is the number of independent variables. Let's look at P. P here is in the bottom, in the denominator. That means that when P increases, when you increase the number of independent variables, this whole part decreases. And when this whole part decreases, the denominator decreases, the ratio increases. And as the ratio increases, this whole bit increases as well. And as this whole bit increases, 1 minus this whole bit decreases. So as you can see, as you're adding more regressors, the adjusted R squared is decreasing. It's going further away from 1. And that is the important part. Also, you can see here what happens when R squared increases. When just normal R squared increases, so this part decreases, right? 1 minus R squared decreases. And that means that this whole part increases. So you've got a battle here. On one hand, R squared, by adding a new variable, you're increasing R squared. So you're increasing adjusted R squared. But on the other hand, by adding a new variable, you're increasing P. So you're decreasing adjusted R squared. And in that sense, it's a fair battle here. If your variable is not good, is not helping the model, then adjusted R squared, this will be an insignificant increase, and this penalization factor will actually drive R squared down, adjusted R squared down. If on the other hand, your new variable that you added is helping the model a lot, then the increase in R squared will be substantial, and it will overwhelm this penalization factor. So even though you'll still get penalized for adding a variable, the increase, the benefit to the model will be so great that even the adjusted R squared will go up. And so that's how the adjusted R squared basically works. It's a very good metric. It helps you understand whether you're adding good variables to your model or not. And we'll be using adjusted R squared throughout this course to make sure our models are robust when we're building them.